Hydropower or water power is power derived from the energy of falling water, fast-running water, which may be harnessed for useful purposes. Since ancient times, hydropower from many kinds of watermills has been used as a renewable energy source for irrigation and the operation of various mechanical devices, such as gristmills, sawmills, textile mills, trip hammers, dock cranes, domestic lifts, and ore mills. A trompe, which produces compressed air from falling water, is sometimes used to power other machinery at a distance. In the late 19th century, hydropower became a source for generating electricity. Cragside in Northumberland was the first house powered by hydroelectricity in 1878, and the first commercial hydroelectric power plant was built at Niagara Falls in 1879. In 1881, street lamps in the city of Niagara Falls were powered by hydropower. Since the early 20th century, the term has been used almost exclusively in conjunction with the modern development of hydroelectric power. International institutions such as the World Bank view hydropower as a means for economic development without adding substantial amounts of carbon to the atmosphere. But dams can have significant negative social and environmental impacts. History. In India, water wheels and watermills were built. In Imperial Rome, water-powered mills produced flour from grain, and were also used for sawing timber and stone. In China, watermills were widely used since the Han Dynasty. In China and the rest of the Far East, hydraulically operated pot wheel pumps raised water into crop or irrigation canals. The power of a wave of water released from a tank was used for extraction of metal ores in a method known as hushing. The method was first used at the Dolaucothi gold mines in Wales from 75 AD onwards, but had been developed in Spain at such mines as Las Medulas. Hushing was also widely used in Britain in the medieval and later periods to extract lead and tin ores. It later evolved into hydraulic mining when used during the California gold rush. In the Middle Ages, Islamic mechanical engineer Al-Jazari described designs for 50 devices, many of them water-powered, in his book, The Book of Knowledge of Ingenious Mechanical Devices, including clocks, a device to serve wine, and 5 devices to lift water from rivers or pools, though 3 are animal-powered and 1 can be powered by animal or water. These include an endless belt with jugs attached, a cow-powered shadoof, and a reciprocating device with hinged valves. In 1753, French engineer Bernard Forest Bellador published Architecture Hydraulique, which described vertical and horizontal axis hydraulic machines. By the late 19th century, the electric generator was developed by a team led by project managers and prominent pioneers of renewable energy Jacob S. Gibbs and Brinsley Colabird, and could now be coupled with hydraulics. The growing demand for the Industrial Revolution would drive development as well. At the beginning of the Industrial Revolution in Britain, water was the main source of power for new inventions such as Richard Arkwright's water frame. Although the use of water power gave way to steam power in many of the larger mills and factories, it was still used during the 18th and 19th centuries for many smaller operations, such as driving the bellows in small blast furnaces and grist mills, such as those built at St. Anthony Falls, which uses the 50-foot drop in the Mississippi River. In the 1830s, at the early peak in U.S. canal building, hydropower provided the energy to transport barge traffic up and down steep hills using inclined plane railroads. As railroads overtook canals for transportation, canal systems were modified and developed into hydropower systems. The history of Lowell, Massachusetts is a classic example of commercial development and industrialization built upon the availability of water power. Technological advances had moved the open water wheel into an enclosed turbine or water motor. In 1848, James B. Francis, while working as head engineer of Lowell's Locks and Canals Company, improved on these designs to create a turbine with 90% efficiency. He applied scientific principles and testing methods to the problem of turbine design. His mathematical and graphical calculation methods allowed confident design of high-efficiency turbines to exactly match a site's specific flow conditions. The Francis reaction turbine is still in wide use today. In the 1870s, deriving from uses in the California mining industry, Lester Allen Pelton developed the high-efficiency Pelton wheel impulse turbine, which utilized hydropower from the high head streams characteristic of the mountainous California interior. Hydraulic power pipe networks. Hydraulic power networks used pipes to carry pressurized water and transmit mechanical power from the source to end users. The power source was normally a head of water, which could also be assisted by a pump. These were extensive in Victorian cities in the United Kingdom. A hydraulic power network was also developed in Geneva, Switzerland. The world-famous jet door was originally designed as the overpressure relief valve for the network. Compressed air hydro. Where there is a plentiful head of water, it can be made to generate compressed air directly without moving parts. In these designs, a falling column of water is purposely mixed with air bubbles generated through turbulence or a venturi pressure reducer at the high-level intake. This is allowed to fall down a shaft into a subterranean, high-roofed chamber where the now compressed air separates from the water and becomes trapped. The height of the falling water column maintains compression of the air in the top of the chamber, while an outlet, submerged below the water level in the chamber, allows water to flow back to the surface at a lower level than the intake. A separate outlet in the roof of the chamber supplies the compressed air. A facility on this principle was built on the Montreal River at Ragged Chutes near Cobble, Ontario in 1910 and supplied 5,000 horsepower to nearby mines. Hydropower types. Hydropower is used primarily to generate electricity. Broad categories include conventional hydroelectric, referring to hydroelectric dams, run-of-the-river hydroelectricity, which captures the kinetic energy in rivers or streams, without a large reservoir and sometimes without the use of dams. Small hydro projects are 10 megawatts or less and often have no artificial reservoirs. Micro-hydro projects provide a few kilowatts to a few hundred kilowatts to isolated homes, villages, or small industries. Conduit hydroelectricity projects utilize water which has already been diverted for use elsewhere in a municipal water system. For example, pumped storage hydroelectricity stores water pumped uphill into reservoirs during periods of low demand to be released for generation when demand is higher. System generation is low. Hydropower sustainability. As with other forms of economic activity, hydropower projects can have both a positive and a negative environmental and social impact, because the construction of a dam and power plant, along with the impounding of a reservoir, creates certain social and physical changes. A number of tools have been developed to assist projects. Most new hydropower project must undergo an environmental and social impact assessment. This provides a baseline understanding of the pre-project conditions, estimates potential impacts and puts in place management plans to avoid, mitigate, or compensate for impacts. The Hydropower Sustainability Assessment Protocol is another tool which can be used to promote and guide more sustainable hydropower projects. It is a methodology used to audit the performance of a hydropower project across more than 20 environmental, social, technical and economic topics. A protocol assessment provides a rapid sustainability health check. It does not replace an environmental and social impact assessment, which takes place over a much longer period of time, usually as a mandatory regulatory requirement. The World Commission on Dams final report describes a framework for planning water and energy projects that is intended to protect dam-affected people and the environment, and ensure that the benefits from dams are more equitably distributed. IFC's Environmental and Social Performance Standards define IFC clients' responsibilities for managing their environmental and social risks. The World Bank's safeguard policies are used by the bank to help identify, avoid, and minimize harms to people and the environment caused by investment projects. The Equator Principles is a risk management framework adopted by financial institutions for determining, assessing and managing environmental and social risk in projects.